Hi friends, let's have a look at problem 2471, minimum number of operations to sort a binary tree by level. This is a daily challenge problem. In this video, we are going to explain a solution based on level order traversal plus get the number of swaps needed to make an array sorted. First, I'll read through the problem statement to digest the requirement, and then we explain the idea, and finally we share the code. Here we are given the root of a binary tree with unique values. In each operation, we can choose any two nodes at the same level and swap their values. So we want to find the minimum number of operations needed to make the values at each level sorted in a strictly increasing order. Here, the level of a node is the number of edges along the path between it and the root node. So here are three examples, and example 3 is very special because in this example, the array in each level is already sorted, so the output is 0. And in the first two examples, the outputs are both 3. Let's look at example 1 in some details. So here there are 4 levels for this tree. So the first level, or level 0, is always in sorted order because it contains only one node or one element in the corresponding array. So in level 1, or the second level, we have 4 and 3. So these two elements are not in the correct order, so we need one swap. So we need one swap in this level. And in level 2, or the third level, we have 7, 6, 8, and 5. So we can use 2 swaps to make it sorted. So you can see the see here, right, for the 2 swaps. And in the level 3, or the fourth level, so 9 and 10 as an array is already sorted, so we do not need extra swaps. So the total number of swaps is 0 plus 1 plus 2 plus 0. That is 3. Let me repeat: 0 plus 1 plus 0. 0 plus 1 plus 2 plus 0. So that is 3. So with that done, let's also look at the constraints. First, the number of nodes in the tree is given by the closed interval 1 and 10 to the power 5. So basically, this defines the problem size, or problem size upper bound. Secondly, the node values are in between 1 and 10 to the power 5. Thirdly, all the values of the tree are unique. So as you are going to see, this assumption is an important one for our coding or our specific treatment. So with that said, let's look at the treatment or idea. So here we are going to decompose this problem to be 2 ingredients. One is doing level order traversal, and the other is to for a array, we want to find the number of swaps to make it sorted. Then for this problem, we just need to sum the number of swaps in each level to get the output. So here are some comments. First, level order traversal is a standard task. We could use list comprehension to do it efficiently. And second, the main effort is to get the number of swaps for an array to make it sorted. This is also not hard in the current problem setting because we can use dictionary to retrieve the indices. So below, we wrote some details for how do we do the swaps. So if you prefer, you can read through or go into details here. Anyway, we're going to explain this part during the coding. So with that said, we are ready to do the coding. So here, as we mentioned, we just need to do 2 things. One is level order traversal, and the other is to find for a array the number of swaps needed to make it sorted. So I'm going to call this level order traversal step 1, level order traversal. For this, I'm going to use list comprehension. So first, I'm going to initialize a list called levels. This list is going to hold the array corresponding to each level in the binary tree. So here I'm going to use level order traversal. So let's have this. So you can interpret it as a queue, but it's not essential. But we need to respect the order. That's the main point. So then we do a while loop. So first we're going to append the array corresponding to the current state of the queue to the levels. That is levels append. So let's use list comprehension. So node value for node in queue. And then we just need to update the queue. So for this, we use list comprehension again. So child for node in queue, for child in node left, node right, if child. So we just retain the ones that are not null. So with that done, so actually we finished get the corresponding arrays for each level. And next, let's write a helper function to get in swaps. So this is actually very standard in some sense. So here we are going to write two slightly different versions just to understand the logic. Let's write in swaps. So we accept a array. So this array is not necessarily sorted. We want to find how many swaps we need to make it sorted. So first, I'm going to make it sort this one. So this S is the supposed positions for each of the numbers in array. Notice that due to the problem assumption, so the binary tree contains unique values, we can assume that the array here involved also contain unique values. So that's the one thing. Another thing, let's initialize a result, which is used to count the number of swaps needed. And here, in order to retrieve the indices, I'm going to use this yi for y in enumerate array, right? And then let's also write the length of this array just for convenience. This variable is not necessary. And then we're going to do a linear scan of this array. If an element is already in the correct position, we do nothing. Otherwise, we need to do proper swaps. So here the main word is swap, proper, right? Let's see how we do that. So for I in range M, right? Let's check if the corresponding position in array and S are the same or equal. If they are equal, it means that the elements are in the correct position. So let's check if array I does not equal Si. It means that the element in array that equals Si is not in correct position. Or you can see the array I, this element not in correct position. So here, let me make some remark to help understand. So I is supposed to hold this number Si, right, from nums from array, but now it holds array I, this number, right? So what we can do first, we can get the index for Si in the array, and then we need to swap the two elements at the two indices are involved. One index is I, the other index is this IDX, right? So currently in array, at index I, the value is here. So at IDX, the value is Si, right? We need to swap. So there are two options. We can first do a swap, then update the indices in dictionary. And also we can first change the index, then do the swap. let's do the latter first. So here, so we want this one, array I, have index ADX, and we want SI, have index I, right? So now we can do the swap, array I, array ADX. So originally at array IDX is the correct SI, right, due to this line. So then what we are going to do is array IDX, array I, right? So each time we do this swap, we're going to increment this result by 1. Then we are ready to return the result. So this is a hyperfunction. Step 3, so we can do summation. This is actually very simple, right? So what we are going to do is like this. So we are going to return. So we can use comprehension. So here we get n swaps for array in each level, in levels, right? So before we make some fine tuning or tweaks, let's first do a check. Yeah, it passes one test case. Now let's look at the generic case. Yeah, it passes all the cases. And now let me make some comments here. So here, first, what we do reassignment. Let's see, or first we update indices in dictionary, and then swap. So this is the thing we are doing here. So actually we can first do swap, then do the reset of the index. So let me copy this function, and then I'm going to use revision, right? Revised version. So but here we can first swap, and then update index, update D. So basically here up to now does not change. So here, right? Then what we're going to do is that because currently we need to swap SI and array I, right? In other words, we need to swap the element at index I and index IDX in array. So what we are going to do is array I, array IDX equals array IDX and array I, right? So once we do the swap, as we mentioned, we need to increment the results by 1. And now, so array I and array index have the corresponding right position. Let's update this one. D array I. So now it's in I, right? And D array index. So notice that originally the array index is SI. So now array I equals SI. It's in the correct position. So this one is in IDX, right? So this is symmetric. Here is array I, this is I. Here is array IDX, here is IDX. So that's it. So this is the second version. Let's try this. We just need to change this to R, right? Let's test. Yeah, it also passes a test case. Now let's look at the generic case. Yeah, it passes all generic cases. So what we want to demonstrate is that, so once we digest the key point, so we have freedom to do the swap and the reassignment or update the indices in different orders. So it's actually, the procedure is actually at our control. So with that said, basically we are done for the current problem. Let me give a quick summary. So here in this problem, basically we want to emphasize how we reduce the problem to be in order traversal, and the task that for a given array we find the number of swaps needed to make it sorted. And then we for the specific coding, so we divide it into 3 steps. So step 1 is the level order traversal. So here we used extensively the list comprehension, but there are other formats of writing, but I feel that this format is clear and it's succinct. And in step 2, so we wrote a helper function to get the number of swaps. So here we can do the swap before reset of indices, or we can first do the reset of the indices and then do the swap. Both are okay, and the procedure is at our control once we really digest the idea. And thirdly, we use the comprehension again to get the output for this problem. So with that said, I guess that's about it for this video. If you found this explanation useful, you're welcome to follow up our channel in YouTube or share this with your friends. With that said, thank you.